All right, good morning, everyone. How are you all doing? All right, good, all right. Sun is shining. I don't know about anyone else, but I was like, yeah, today's gonna be a good day. Bounce back. Just me? Okay. All right, well, I hope you have a good day anyway. Okay, does anyone have any questions before we get started? All right, cool. So home stretch, we are, exam 2 done. We're coming to the end of the semester. So actually, let's look at the syllabus. It's been a bit since we've looked at all of these. So we are right now, what day is today? The 8th. So we're right here. Should have known that right after the exam. So there's no class on Monday. So that's a nice little break that we're gonna have. And then, but do remember that you need to do the post-exam 2 survey. Hopefully we won't have as many hiccups as we did with the pre-exam 2 survey. There were a lot of issues with the completions. So like I notified a bunch of people that you didn't complete, and then you all emailed me back saying, yes, I did. And basically I got an updated report that reflected that pretty much everyone did complete it. So I meant to send out an email yesterday, didn't have time. So I'm gonna send out an updated email today to let you know that like, yes, I did actually receive it, you are all good, that the pre-exam 2 survey was taken care of. So there's that. And then there is no homework this weekend. There's no quiz this weekend. So we do have a little bit of break with the extended weekend anyway. But if you want to look ahead and start the chapter 12 stuff, cool. That's a nice head start as we're going in. We only have a couple more weeks, and yeah, we only have 3 more homeworks, 2 more quizzes, 1 more exam. Cool. Any questions about like the schedule or anything? Cool. So let's start our alkene reactions. So this is our last major like reaction mechanism. So remember that we have the 3 reaction classes. We have that substitution where you're going from one functional group to another functional group. We had our elimination, which was where we were going from a very similar looking starting material, but making an alkene. Now we're going to get into our additions, where we're going from that alkene to having some new functional group added in. All right, so that's this last part that we're trying to get at. The last main mechanism reaction class that is organic chemistry. So we've already done some additions. We did additions with our carbonyls, and that was to make our alcohols. So these additions are going to be with our alkenes, so carbon-carbon double bonds, and our alkynes, the carbon-carbon triple bonds. These are going to act as nucleophiles. So unlike our carbonyls, where you had that polarized pi bond, those were our electrophiles where we attacked the carbon of the carbonyl. Our alkenes, that non-polar pi bond, that's going to act as a nucleophile because that is a concentration of electron density. So now for all of these reactions, our curved arrows are all going to start at the pi bond and go out to the other thing, right? So it's going to be the alkene attacks whatever reagent. We are going to have a lot of reagents. So if you haven't started your reaction notebook yet, you're definitely going to want it for your addition reactions because we have a lot of reagents, a lot of different compounds to look at. Try to find the similarities and differences between them. So if you can try to keep them organized, then it won't be as overwhelming, right? So I get told by a lot of students that it feels like we all of a sudden are like running to the end where we've picked up so much speed. And that's one, because you already know like inherent reactivity, but more so, it's just because we're gonna, like everything is just like, here's this reagent, there's that reagent, there's that reagent, there's that reagent. It just kind of feels like a list. And so it feels like we're doing a lot more, but it's just that they all just kind of look a little different, I guess. So it's not so much like any more or less content necessarily in terms of like the grand scheme of things, but it's gonna look a little, they're all gonna look very different. So the like biggest recommendation I can do is focus on the similarities. So I'm going to group them based on their mechanisms to try to help you not have as much to memorize. So if you can identify our carbocation, our anti, our syn, and our oxidative cleavages, then that's going to tell you, like, if you know all these reagents go through carbocation mechanisms, then they're all going to do the same thing, right? So if you can just kind of group them, it's going to make your life a lot easier. Our carbocation mechanism is going to go through a carbocation. You know that you will do a carbocation mechanism because we're going to have that strong acid, which that tracks, right? Like when we had our alcohols and we added strong acid, we made carbocations usually, unless we were just trying to get to a primary. But like if you just in general, like with our ethers, that's a better analogy. With our ethers, you had that strong acid, we were making that carbocation. So you see strong acid, we're going to make a carbocation. So we have two main reaction names we're going to look at. There's the hydrohalogenation and the hydration. Hydrohalogenation is adding a hydrogen and a halogen. And so it's going to be where our halogen is going to end up on the more substituted side, and our hydrogen is going to end up on the less substituted side. We are going to call this a Markovnikov addition. Which we will talk more about the Markovnikov addition in a hot second. All right, so the hydrohalogenation adds a hydrogen and a halogen. Halogen goes on the more substituted side. Our hydration is going to be the opposite of that condensation. So hydration is now using water, like if you're hydrating yourself, you're drinking water, you're taking water on. Hydration is going to make our alcohols. So for the hydration, here we're seeing that alcohol from the water on the more substituted side, and our acid is again putting the hydrogen on the less substituted side. That is also a Markovnikov addition. Our general mechanism is going to be the same for both of these, where it's going to be, you have a strong acid, protonate something. The best thing to protonate will be our alkene. So we're going to start at the pi bond and go to the hydrogen. So we start at the pi bond, go to the hydrogen of the strong acid, and then give the electrons to that conjugate base. We end up with our carbocation. This hydrogen is right here, going on that less substituted side. And now our nucleophile can attack our electrophile, right? To give us our desired product, give us that Markovnikov regioselectivity. So all we did was an acid-base reaction, a Bronsted acid base, and then a Lewis acid base, which is just nucleophile-electrophile reactivity. So it was Bronsted acid base, make the carbocation, have the nucleophile attack the carbocation. All right, I keep saying this word Markovnikov. So let's actually say, what does that mean now? So our Markovnikov addition is describing our regioselectivity. So remember, regioselectivity is saying which region reacts, right? Which region is going to selectively react. So the way to remember Markovnikov, like the trick to remember this addition, is saying what has gets. So that's kind of a quick translation of the Markovnikov, is our trick to remember it. What it's saying is what has the most substituents gets the new substituent. So our new substituent X goes on the more substituted carbon. That is Markovnikov. Or you could also think of it as the side with more hydrogens gets the hydrogen. Right? What has gets. What has more substituents gets the new substituent. We will have anti-Markovnikov, which is just the opposite. So where you get the X on the less substituted carbon. We will have 2, I believe, reactions that'll be anti-Markovnikov, but our carbocation mechanism will always be Markovnikov. So why is that? Why do I see this observed regioselectivity? The answer is carbocation stability. So if we consider that alkene again, and I imagine I could have that alkene attacks the acid, and my intermediate could either be the hydrogen goes on the left, carbocation on the right, or I could go hydrogen on the right, carbocation on the left, right? You could do it either way, right? There's nothing initially stopping you from saying, do I put the hydrogen on the left or the right? And hopefully when you do practice problems, you will ask yourself that same question where you're like, which one goes where? And when in doubt, draw them both. Whichever one's more stable, that's the one you take. And then if there's no difference between them, then you get both of them. But when we look here, I see a secondary carbocation on the left side, like when the hydrogen went to the left. When the hydrogen went to the right, I get a tertiary carbocation. So remember, we will always make the most stable carbocation. That's why this is what we're going to make. Always make most stable carbocation. So then that's why our new substituent always adds to the more substituted side, because that's where we get our stable carbocation. That's where we get our electrophilic site. So our new group is always going to add to that side because of our mechanism, because we're always making a carbocation, so that's where the nucleophile will attack. When we think about our stereoselectivity with our alkene additions, because our alkene is planar, right? How do I know my alkene is planar? It's sp2 hybridized. sp2 is trigonal planar. Planar means flat. So if both of these are these flat triangles, then the whole molecule is flat. So sp2 is going to be that trigonal planar that is flat. So I can attack from either the top or the bottom, right? I can add stuff to the top or the bottom. If your hydrogen and your halogen are on the same side, so here, I guess we'll make, imagining like Y is H, I guess, to try to keep it consistent. Because I'm trying to illustrate that generally this is the stereochemistry for all of our alkenes, but applying it to the carbocation mechanism, Y would be H. So Y could be on the top or the bottom, so your H could be on the top or the bottom. Right, so I'm seeing there's that hydrogen. I'm just keeping it on the right-hand side to be consistent. So it can either be on the top or the bottom, right? Top or bottom. That's the hydrogen can add to either side because the alkene starting out is planar. Because I go through a carbocation intermediate, that X, that new halogen, can also add to the top or the bottom. So that means that if my hydrogen's on the top, my halogen can come also from the top or the bottom. And then when the hydrogen's on the bottom, the halogen can also come from the top or the bottom. So what we're going to see is that because we're going through a carbocation mechanism, we're just getting really no stereoselectivity, is the point. Because we're an sp2 starting material and carbocation intermediate, which is also sp2. So we can attack the top and the bottom. So there's no stereoselectivity for our carbocation mechanism. We're going to describe the products where our substituents are on the same side as syn. So a syn addition is saying that we are adding to the same side. That the two groups added to the same side. So the hydrogen and the new substituent added to the same side. Anti is going to be if they add to opposite sides. So now the hydrogen and the halogen are on opposite sides. So with our carbocation mechanism, you will see both syn and anti addition. You get the mixture of both of them. So this should also kind of give a quick highlight, an indication that like, if those mechanisms I told you, we had carbocation, syn, anti, and oxidative cleavage, those were the four mechanisms we're going through, then carbocation is giving us a mixture of syn and anti. So then our syn mechanisms are going to give us syn products. Our anti mechanisms are going to give us anti products. So those mechanisms are going to describe what our products are looking like, right? So the carbocation mechanism, we're getting a mixture of everything. But that's for stereochemistry. Regioselectivity is that it's always the Markovnikov addition, where what has gets. The more substituted side gets the new functional group. So that's the summary of our carbocations. So we said that the two carbocation mechanisms that we have are the hydrohalogenation and the hydration. So we're adding hydrogen and either a halogen or an OH group. It will always be a Markovnikov addition. There is no stereoselectivity. And we're going through that carbocation intermediate, so we always must watch out for carbocation rearrangements. Just like with SN1, just like with E1, that is still a valid statement. So we still have to watch out for this. We must watch out for carbocation rearrangements. So if I imagine I'm doing this reaction where I'm going to add hydrochloric acid to this. Start out, alkene attacks the proton, electrons go on to chloride. To figure out which side gets the hydrogen, actually you tell me, does the hydrogen go on the left or the right? The hydrogen will go on the right, the carbocation goes on the left. So when we look at this, there are 2 hydrogens on the right side, 1 hydrogen on the left side. So there's going to be those 2 hydrogens on the right. The new hydrogen goes with the side that has the more hydrogens, what has gets. Also, when in doubt, even if you're like, I don't remember Markovnikov, think about what are your 2 products. That's the one product. This is the other. Because you either say, all right, if the hydrogen went on the right, then the carbocation's on the left. If the hydrogen went on the left, then the carbocation's on the right. Which of these is more stable? The top one or the bottom one? Top one, why? It's a secondary carbocation as opposed to a primary. We're not going to make the primary carbocations. So we're going to, I guess we could leave it and we'll just cross it out. So we get to our carbocation, we made the more stable between primary and secondary, but we still must make the most stable carbocation possible. So the fact that I have a quaternary carbon next to a secondary, I'm going to be able to have this alkyl shift. Now that I'm at my tertiary carbocation, now that my carbocation is the most stable possible, now my nucleophile can attack. Just like with SN1 and E1, you must make the most stable carbocation before anything else can happen. Before your nucleophile can attack, you must make the most stable carbocation. Oops, forgot the methyl. Cool. So we did acid-base chemistry, carbocation rearrangement to make our most stable carbocation, and then nucleophile attack. Just like every time you see a carbocation, stop, check for the rearrangements. You must make the most stable carbocation before anything else can happen. All right. Do we have any questions about the carbocation mechanisms? Okay. So the main, and actually I'm going to add this right here, because usually by the time that we finish all of our reagents and all of our reactions, like we forget how we knew that we did a carbocation one. So to remember, we're doing the carbocation because of the strong acid. So we need to know what the strong acids are. So the indicator, how do I know to do this? You see that strong acid. That's what told us carbocations. Strong bronzed acid, sulfuric acid, hydrochloric, hydrobromic, hydroiodic. That told us carbocation. Okay. Next up, we're going to have our anti-selective mechanisms. So anti-selective, meaning that it's describing the product that we're going to see. So we're going to see that our two groups are going to end up on opposite sides of our molecule. I also like to call these the onium ions because that's describing our intermediate. So anti describes the product. Onium is going to describe our intermediate. So it's kind of like how carbocation was describing the intermediate. Onium ions is going to describe the intermediate. So all of these are going to go through a three-membered ring with a positive charge. So that's the onium. So we're going to have, this is known as a halonium because it's a halogen in a three-membered ring with a positive charge. So if you have chlorine, it will be a chloronium ion intermediate. If you have bromine, it's a bromonium ion intermediate. Iodine, iodonium ion intermediate, right? When we have mercury, merconium ion intermediate. That's why I like to call them the onium ions intermediate. So the onium ion is our anti. And we're going to have 3 reactions for this. We have our halogenation, which is going to just be adding halogens. Our halohydrin, which is going to be adding a halogen and hydrating. So it's going to add both a halogen and an alcohol. And our oxymercuration demercuration, which is going to be making alcohols. So it's going to be using mercury to do it though. So we're going to go Hg to OH. Those are 3 anti-mechanisms that we need to know about. So halogenation is just adding halogens. So the difference here, and this is really, we're mostly just doing this with bromine and chlorine. So, no, we'll do the mechanism on the next slide. We'll go through that in a hot second. The thing that I really just want you to see at this point is the products. We see that they are adding on the opposite sides, right? That's the anti, is that they're on opposite sides, and those are the elements that we're adding. Our halohydrin and the oxymercuration demercuration, our OH is going to add to the more substituted side for both of these. The reason why is going to be because of the mechanism. All right, so let's look at the mechanism. So we are still going to start. Alkenes are our nucleophiles. We start at the pi bond and go to whichever side is going to be electrophilic. So in this case, it's both bromine, so bromine. You pick one, whichever one's happier or makes you happier, pick that one. We're going to our electrophilic side, and we're going to have to break that bond. The difference here, where our mechanism deviates. So far, we're looking exactly the same as if this was like HBr, right? We're doing the same thing. The difference between Br2 and HBr is that bromine that we are attacking also has a lone pair of electrons. Hydrogen doesn't have a lone pair, so it just gets attacked and it just flies around. Bromine has a lone pair. Bromine is going to attack back onto our alkene. So where it's different is we get this extra arrow going from the bromine, from the lone pair, the bromine that we're attacking, to our more electrophilic side, to the more substituted side. That's where we're deviating between our carbocation mechanism and our anti-mechanism. The reason why is because you have that lone pair. So essentially what's happening is as a carbocation is like theoretically forming, as that becomes more delta positive, you have a lone pair right next door. And remember that those three-membered rings form very quickly, right? Like epoxides, we said that epoxide ring forms really quickly. The three-membered ring forms the fastest. Having that lone pair right next door, let me draw out all the words that I'm saying. So if theoretically we're getting this bromine here, and we're getting this carbocation forming, I have that lone pair. I have a nucleophilic site right next to my electrophilic site. And three-membered rings form very quickly. So quickly that we're not going to actually see this intermediate. Actually, we'll say what happens. Forming the three-membered ring is so fast, we never actually see the true, like, formal carbocation. Like, it never actually becomes a naked carbocation, because as it gets that partial positive, it's just that bromine's like right there, ready to go, right? So it's just adding on immediately. So it is that alkene attacks the bromine, electrons go onto the other bromine, but because that lone pair is right there and three-membered rings form so fast, it's just coming right back on it. It's just on the side that would have had a carbocation, that lone pair is just closing down. So we right away get to our three-membered ring, that bromonium ion intermediate, or chloronium ion, or iodonium ion, or merconium ion, whatever your thing is in the three-membered ring, is that onium ion, three-membered ring with a positive charge. And the key difference is having that lone pair. It attacks back down. Now, you will have it both attack from the top and the bottom. So we will still see the bromonium ion on the top and the bottom. That's stereochemistry because we start flat, so you always get both the top and the bottom. The next attack, that nucleophilic bromide, is now going to, so this is my nucleophile. That bromonium ion is now my electrophile, right? Just like how my epoxides were electrophiles, right? But with a positive charge. So our bromonium ion intermediate is acting like our protonated epoxide, except there's no strong acid there necessary, because it's just that bromine already has a positive charge, so it's already like ready to go. So that nucleophile is going to do that like SN1 type reaction, where it's going to attack the more substituted side. If I can get around all the things that I've drawn. It's going to attack the more substituted side and pop open the ring. Right, so it's acting like that SM1 type mechanism that we saw with our epoxide reactivity. But there's no strong acid here, right? Because that's the key difference. If there was strong acid, we're doing carbocation. There's no strong acid here. Because that three-membered ring is blocking one side of our molecule. So like this bromine, that bromonium ion, that's blocking the top of that molecule. So my nucleophile has to come from the opposite side. So that's why it had to be on the bottom. So if this is, that's the nucleophile, it's coming from the opposite side of wherever the original bromine was adding. So the product here would have that bromine on the top, this bromine's on the bottom. Can't draw triangles apparently. Your nucleophile will always be coming from the opposite side. Because the ring blocks one side. That's why we see the anti-stereoselectivity in the product. That's why they're always on opposite sides, because you go through this onium ion intermediate. You go through that ring, the ring blocks one side, so then the nucleophile has to attack from the opposite side. So you always get this opposite side opens the ring, or it comes from the bottom and the ring pops open that way. So my stereoselectivity is that it's anti, and you do see both products. Bless you. So my stereoselectivity is that I am anti. There isn't really any regiochemistry here because they're both bromine. So like there isn't a difference between the two groups that are adding. They're both bromine, so there's not really any like regiochemistry consideration. But we do know though that in that nucleophile attack in the second step, that nucleophile always goes to the more substituted side, right? So if this were, I'm running out of colors, so I apologize if this is looking disastrous. But if this had been, what's less electronegative than bromine? Iodine? Let's do, so if this is like iodine and bromine, then your iodine is the one that's partial positive. So then the iodine is what would have made the ring, and then the bromine would have ended up, the more electronegative atom would end up on the more substituted side. So when they're the same element, there's no difference. But if they're two different halogens, then whichever one is more partial positive ends up forming the ring, because that's what we attack. And then whatever is the more nucleophilic side, the more delta negative side, that ends up on the more substituted side of our double bond. So just because I wrote that out to make sure that makes sense, I'm gonna. So if I have this, my products are going to be yeah, whatever, it'll be this. So that's what I'm saying. Just like how if it was like HBr, the hydrogen went to the less substituted side. It'll be the same thing if you have like iodine and bromine. Whatever is more delta positive, that will be on the less substituted side. Whichever is more delta negative is on the more substituted side. So that's the halogenation. Our halohydrin is going to do the same first step, right? We're still going to do alkene attacks a halogen, kick out water, or kick out the bromine, sorry. Lone pair attacks the more substituted side. So we get to our bromonium ion intermediate. Step one, still the same. The difference here is that if you have bromine, and normally this is actually usually done with chlorine, but if you have either bromine or chlorine, remember that bromine and chlorine are going to be small enough. Bromine gets a mixture of solvent shell / can be nucleophile. That's why chlorine is best. But chlorine gets that tight solvent shell. So if you're in water, then your bromine and your chlorine are not going to be your best nucleophiles anymore, right? Water becomes your better nucleophile. So water now is going to be what attacks the more substituted side. So water is the better nucleophile because of our solvent shell. And there are billions upon billions upon billions upon billions more of those water than that bromide, right? If water is your solvent, you have so many more of them than just that one little bromide. So that means that you're gonna have a whole bunch of waters all around here, that bromide's like chilling up here. It's going to take a lot longer for that bromine to wiggle its way through the water and get to that carbon than water that's like already chilling right here. So because there's so much more water also then outcompetes the bromine. So the solvent shell slows down the bromine, and there's more water than that bromide. So probability is on its side. Right? So if waters are solvent, there's just so many more of them that it is now going to act as your nucleophile to outcompete that one little bromide that's got to wiggle its way around to actually find the electrophile. Water is just all set up. There's so many of them, it's just already right here, ready to go, ready to react. So that's why water acts as the nucleophile, attacking the more substituted side. And then you just need to do acid-base in order to get it neutral. So that's the difference for the halohydrin, is just you have water as the better nucleophile. So the difference between your halogenation and your halohydrin is purely, do you have water? Is your solvent water or an alcohol? Yeah. Yeah, you should still have equilibrium arrows for every time you do acid-base reactions. Yeah, I was lazy, but that's a good point. We should add those in. Which actually, for the carbocation mechanism, roll back up. Anywhere where we did acid base, yes, we still need to keep those equilibrium arrows. Thank you. All right. Yeah. Yeah, so if you, that's a great point. If you have hydroiodic acid, then, well, one, you have HI, so you would actually do a carbocation mechanism. But if you have iodine and water, because if you have HI, that equals carbocation. So if you have I2, that iodine is still a better nucleophile. You're going to get a mixture of products, though, because the solvent can still potentially outcompete, but the iodine is the better nucleophile. You're absolutely right. So with that's why we don't do this reaction with I2 in water, because you get a mixture of iodine and water competing with each other, because the iodine doesn't have that solvent shell. You're absolutely right. Yeah. So if you just use I2 and water, you get a mixture of the iodine and the alcohol being incorporated. So you'd have both I and OH there. Not simultaneously, but you get both the the halogenation product and the halohydrin product, because there is still a little bit of that probability. But the iodine is absolutely now in competition. So we just don't do it with iodine, is the takeaway. Okay. And I'm going to write plus diastereomer. I'm going to tell you right now, on the predict the products for the final exam, you will not be able to write plus diastereomer, because the point of the exam will incorporate, do you also know what stereochemistry is? And so I'll want you to actually draw the product that is the diastereomer. But for now, I'm okay if we're a little lazy and just write plus diastereomer. But if you want to be in good practice, let's just draw it. So it's just the fact the OH is still on the left, the BR is still on the right. It's just that you get both the top and the bottom addition. Actually draw the diastereomer, or actually, in this case, an enantiomer. So the reason it's an enantiomer is because those two methyls are the same. So there's actually only one chiral carbon. All right. Are we cool with our halogenation halohydrin? Yeah. Yeah, so for the carbocation one, yeah, you're either drawing out, where'd it go? All four of these, or we can use our line notations to represent that both the wedge and the dash would exist there, right? So if you draw this, well, that's also not a chiral carbon, but pretend this was a chiral carbon, then, well, that's still not chiral, whatever. Pretend it is a chiral carbon. If you draw that straight line there, that tells me you know that it's both a wedge and a dash. So you can use those lines effectively to not draw each individual structure. But if you are like, oh, I want to be really careful, then yeah, you would draw all 4. But we can summarize them by using straight lines instead of having to draw wedges and dashes on every single one. Okay. Any other questions about our hydration or the halogenation or halohydrin? Okay. Our oxymercuration demercuration is still doing the same sort of thing. It's just going to look weird because we have mercury. So if you see that Hg, the important thing is that it's a mercury 2 salt. So it's Hg2 plus. So I don't care what my counter ions are. It could be sulfate, chloride, whatever. I don't care what the counter ion is. I just need this mercury to be a 2 plus. That's the requirement for this reaction. And it's still going to be alkene attacks the most electrophilic site, which is the metal, which has the 2 plus charge, right? It's cationic. So it's going to attack the metal. We're going to kick out whatever is that counter ion, whatever is that anion. We kick that out. And then the mercury has a lone pair to attack back down. So it's the exact same thing as our halogenation. It's just now we have mercury, so it looks a little weird. That makes our merconium ion intermediate. So I also then need water to come in and pop open that ring. Just like our halohydrin, where water is the best nucleophile in solution, so water is what's going to come in, open that ring, and then we just need to do acid-base in order to get it neutral. So all of those steps are exactly the same as everything we've talked about so far. Our last step is the demercuration. So oxymercuration is we're adding oxygen and mercury. We added oxygen and mercury. Demercuration is I got to get rid of that mercury because I don't want mercury. That's our next step, which we'll talk about that on Wednesday because we don't have class on Monday. All right. Have a wonderful day. Try to relax a little bit. Enjoy the sunshine.